Welcome to the flock. Let's dive into identifying conjugate acids and conjugate bases, along with acids and bases, according to Bronsted-Lowry. If figuring out which chemical is the acid, the base, the conjugate acid, and the conjugate base is confusing for you, stick around to see how it's done. In the previous lesson on acids and bases, part 1, we learned that according to Arrhenius, an acid is something that creates hydronium ion when dissolved in water. That's H3O+, this guy right here. And according to Arrhenius, something that's a base is something that would produce hydroxide ions, OH- in solution. However, if we look at the reaction between water and itself, H2O plus H2O, we see that it yields both hydronium ion, the acid, and hydroxide ion, the base. So according to Arrhenius, water is both? Absolutely. It's important to note that water is amphoteric, meaning that it can act like an acid or a base depending on the situation it's placed in. This is important to note for Bronsted-Lowry and all other future acid-base questions, because sometimes you'll see water as one of the reactants. And yes, it will act like an acid or a base, as funny as that may seem. You can remember the word amphoteric like amphibian. An amphibian can be both on land and sea, just like water, being amphoteric, can act both as an acid and a base. It does this by switching between acidic and basic properties all the time. So that glass of water you're drinking out of your hydro flask, that water in there is literally both acidic and basic all the time. This property or this process is called autoionization. Just like your automatic car can shift automatically between gears, water is shifting between the gears of acid and base on its own, creating both hydroxide ions and hydronium ions. Now, it's also important to note that Arrhenius does not work for all scenarios in identifying acids and bases. This is why Bronsted and Lowry came in the 1900s to give us a new definition. Let's see if you can figure out what the definition, according to Bronsted and Lowry, would be instead of Arrhenius. If we're looking at the equation between ammonia and water, notice that there's a little arrow drawn from the lone pair on nitrogen grabbing the hydrogen off of this water molecule. When it does so, these electrons holding the hydrogen and the oxygen together shift over and live on the oxygen instead. I know that by looking at the products. On the product side, I see that those electrons are right here that shifted over between the bond of hydrogen and oxygen, and I also see that the lone pair of electrons are now bonded to the hydrogen that it took from water. In chemistry, we know that ammonia acts as a base. So based off of what this base does with water, we could say that bases are actually chemicals that take hydrogen atoms, we also call them protons in chemistry, from another chemical. And since it's taking the H, and since there's a base, there has to be an acid on the flip side. So in this case, water would be acting as an acid, actually. Remember, it's amphoteric. It could be either an acid or a base, depending on the situation it's placed in. Since it happens to be placed with a base, ammonia, it has to act as the acid. So then the official definition that you need to know from Bronsted-Lowry is that an acid is a proton, i.e. an H atom donor. It gives away its H, whatever H it has to give, it'll give. And according to Bronsted-Lowry, the base is the one that accepts that H from another chemical, i.e. it steals it or wants to take the H from the other chemical. So from the previous lesson, we learned that bases are also blue on the pH scale, and bases taste bitter. In this case, we can also think of bases as bullies because they're the ones that like to steal the lunch money, if you will, or steal the protons, the H atoms. So you can remember that bases are bitter, blue bullies. There's also a little jingle that you can keep in your head to remember the difference between the two. In chemistry, the difference between an acid and a base is a base accepts a proton which an acid donates. So jumping back to water then, according to Bronsted and Lowry, we know that if acids donate, give away their proton, and bases are bullies because they take away a proton from something, here are two examples where water will either act as a base or an acid. For the first example, we see hydrochloric acid, HCl, right here, and we see water, H2O. The water's lone pair here on oxygen is going to reach out its arm and take the hydrogen. So you can kind of think of those arrows as a little hand coming over and grabbing the H off of the HCl. Obviously, it doesn't have a tiny atomic hand, but we're just pretending here, okay? So that arrow is going to reach over and grab the H off of HCl, and that creates H3O plus on the product side, because we went from something that had 2 H's to something that now has 3. Remember that H3O plus is called hydronium ion. Once that H is taken, these bonded pairs between H and Cl have to go somewhere. So these electrons are now just going to shift over onto chlorine, giving us a full negative anion in solution. Since the water is a bully in this scenario, and it takes an H or it accepts an H, depending on how you want to think about that, I like to think of it as being a bully and stealing. So it's stealing the H off of HCl. It's acting as a base in that scenario. That means that the HCl must be the acid. They're always going to come in pairs. Where there's a base, there's an acid, and where there's an acid, there's a base. In the bottom scenario, this is the same one we looked at earlier where we had ammonia. And the lone pair on ammonia reaches its hand over and takes the H off of the water molecule this time. Those electrons that were bonded have to shift over onto the OH, creating hydroxide ion and ammonium, NH4 plus 1. In this case, since the water is giving away the H or donating the H, it's acting as the acid, meaning that the ammonia has to be acting as the base. Let's give this concept a go in full strategy. Let's try and figure out which of these two reactants is either the acid or the base. Remember, on the reactant side, wherever there's an acid, there must be a base, and wherever there's a base, there must be an acid. They always come together for this acid-base reaction. And the way that we can identify who is doing what, who's taking the H, who's donating the proton, we have to compare the reactant side to the product side. So we're going to link whatever chemical looks like the one in the reactant side to the one that it looks most similar to in the product side. Let me show you. So if we're looking at this first one, HCO3 minus looks like Cl minus, or does it look more like H2CO3? Of course it looks like H2CO3. There's not even a Cl in that reactant. So we're going to link up the HCO3 minus with H2CO3 in the products. So the idea here is that we're linking the reactant side with the one it looks like in the product side, so we can see what happened. If we compare our HCO3 minus from the reactant side to our H2CO3 on the product side, we notice that it gained an H. Where did it get the H from? If we look at the HCl on the reactant side, and then we compare it to the product side, we see it's missing that H. The Cl is all alone now. That means that the HCO3 minus must have taken the H from the HCl, just like we saw in the previous examples with the arrows drawn out. So here we can say that HCO3 minus was the bully. It's the one that took the H from HCl. Since it's the bully, that means it must be the base. And since HCO3 minus is the base, by process of elimination, HCl must be the acid. We can reconfirm this in the fact that it has an H on the reactant side and is missing the H on the product side. Therefore, it donated or gave away its H. That's what acids do. Remember, in chemistry, the difference between an acid and a base is a base accepts a proton which an acid donates. Let's use the same logic for the bottom equation. We have HC2H3O2, and that clearly looks more like the C2H3O2-. We also have H2O, and we're going to link that with H3O+, since that's what it most looks like. When we compare the H2O on the reactant side to H3O+ hydronium ion on the product side, we see that water gained an H. In this case, whenever you gain an H, that means you had to take it from somewhere. That means you had to be a bully. So water here is acting as the base. It's a bully. It took the H from HC2H3O2, because notice it's missing that on the product side. Since HC2H3O2 lost that H, it gave away the H, it donated the H. That means it must be acting as the acid. Now that you've seen me do it, go ahead and give this one a try yourself. Pause the video here and see if you can identify acid and base on the reactant side. Go! All right, let's check your answers, see if you got it right. All right, hopefully you got these as your final answer and were able to track where the H's were going, if they were lost or gained, according to each chemical to determine if it was an acid or base, respectively. So now that we know how to identify the acid and base on the reactant side, what about this whole conjugate acid and conjugate base stuff? Well, just like we said, there's always going to be an acid paired with a base. That's true for over the reaction line as well. If you have an acid in the reactant side, it will be paired with a conjugate base on the product side. Likewise, if you have a base on the reactant side, it will be paired with a conjugate acid on the product side. So linking them together, as we started doing, is actually an easy way to figure out its conjugate pair as well, once we know if it's an acid or base on the reactant side. Just thinking about what the word conjugate means, like in Latin for husband and wife, conjux, we know that it means a pair or a mated pair in that case. But in chemistry, that conjugate would literally mean that it's the pair created from the reactant side. So again, there's going to be an acid paired with a conjugate base and a base paired with a conjugate acid. So using the same exact equations we used earlier, let's see if we can figure out which of the products is the conjugate acid and which one is the conjugate base. So just as we determined before, the HCO3- was the base because it's a bully and it took the H from HCl when we compare it to the product side. That means that the chemical that HCO3- is linked to on the product side, that H2CO3, is going to be its conjugate acid, and we'll abbreviate that as Ca. Likewise for HCl, we knew that it was an acid because it lost its H on the reactant side. That means its pair on the product side must be the conjugate base. Notice that the conjugates can only happen on the product side. You're never going to see the word conjugate on the reactant side. And notice that our premise still holds true. Both on the product and reactant side, we have an acid and a base. What's really cool about this is that this reaction could go backwards if it wanted to. We have a base and an acid in the product side. What's stopping this chlorine from having its lone pairs reach over and grab one of the H's off the acid? That would literally just mean that the products would shift back and turn into the reactants again. Pretty cool, huh? So now in the bottom equation, we know that water was acting as a base because it was a bully and it took an H from the HC2H3O2 molecule in order to become hydronium ion, H3O+. So if it's a base on the reactant side, it must be a conjugate acid on the product side. Likewise, we see that HC2H3O2 is the acid because it donated or gave away its H, and its product link must then be the conjugate base, of course. You can also check your reasoning here and notice that the C2H3O2 molecule doesn't even have an H in the front to donate. It would be impossible for us to classify it as an acid. If there's no H's given, you can't be an acid. All right, now that you've seen it done, I have full confidence that you can do it yourself. Go ahead and pause the video here and see if you can identify the conjugate acid-base pairs. All right, let's check your answers and see if you did it right. Hopefully you got those answers and you understood how to get there. Always start by linking your reactants and your product that looks similar to the reactant and identifying who's taking and who's giving those hydrogens. Another point of confusion for a lot of students is the difference between strong and weak acids and bases. Now, this doesn't have to do with like muscle strength, like you are bodybuilder of acids, bases. No, strength here has to do with how many H's you give. If you're a strong acid, you give away all of your H's to anyone, particularly a base, obviously, who will take them. And if you're a weak acid, you only give some of your H's, but not all of them, so you give them begrudgingly at best. But this does not mean that a weak acid is less scary or less caustic than, say, a strong acid. For example, hydrofluoric acid is classified as weak. However, if you were to put your hand in a vat of hydrofluoric acid, you wouldn't really have much of a hand anymore. It doesn't mean it's less dangerous or less scary. It's still a scary chemical, dangerous chemical. But the difference between strong and weak is purely how many H's it gives up in solution. Likewise, with a strong base and weak base. A strong base will take all of the H's away from anyone, i.e. an acid, who will give them, and a weak base will only take some of the H's, not all of them. There are also acids that have more than one H to give. If they only have one H to give, they're called monoprotic. Examples of that would be like nitric acid or HCl, hydrochloric acid. You can also have two H's to give, like sulfuric acid, H2SO4. Or you could even have three H's to give, which would be like phosphoric acid, H3PO4. However, each time you remove a proton, something that's positively charged, i.e. that hydrogen atom, it becomes more and more difficult to take the next proton off. That's because each time you remove one, you become more negative. And as you become more negative, you want to hold on to the positive even stronger. So for example, if we were going to remove the H's from the triprotic molecule, phosphoric acid, it would become less and less favorable with each H that we rip off of it. That first H would be really easy to take, not so much as you go down the line and try taking all three. Before you move on to part 3 of our acid-base series, make sure you test yourself before you wreck yourself and identify the acid, base, conjugate acid, and conjugate base for the following 2 chemical equations. If you'd like to know if you got your answer right, please comment below and I'd be happy to let you know. In this lesson, you learned that the difference between an acid and a base is a base accepts a proton which an acid donates. And you also learned how to identify a conjugate acid and conjugate base pair, along with some tidbits about acids themselves, like how they can be monoprotic, diprotic, or triprotic, i.e. polyprotic, meaning they have many H's to give. And we also touched on the difference between strong and weak acids and bases. Please give this video a quacks up and subscribe to my Duckonta channel for some more quacky content. Hope to see you soon. Have a ducky day.
No ducks, no glory.